Today I'm going to present a Ruca methodology, which is runtime configurable approximate circuit with self-correcting capability. Here is the overview of my presentation. Let's start with the objective of our methodology. Approximate computing is an emerging computing paradigm which offers improvements on chip area power consumption by trading off accuracy. It can be widely used in areas such as image processing, machine learning, or signal processing. Those applications can inherently tolerate a small amount of errors in their outputs, and different applications of approximate computing expect different levels of inaccuracy. The objective of Ruca is that, for a certain functionality, we would like to design a single approximate circuit that works for multiple applications with multiple accuracy levels. In this case, by adjusting accuracy levels at runtime, we're able to optimize power utilizations. For example, in this image, we design one approximate adder that works for all three applications, and as error threshold increases, the circuit is expected to save more power. Now, I will introduce Boolean matrix factorization and its application on approximate computing. A Boolean matrix is defined as a matrix where all elements are zeros or ones. Boolean matrix factorization, which is also known as BMF, aims to factorize a Boolean matrix into two, where multiplications are done using logical ANDs and additions using logical ORs. BMF algorithms fix the best factorization, where the difference between the input matrix and the product of factorized ones is minimized. Here, we define F, the number of columns in matrix A, as factorization degree. An approximate computing methodology based on BMF has been proposed. Since the truth table of the circuit is effectively a Boolean matrix, we may approximate the circuit by factorizing its truth table. Firstly, the input circuit is simulated and its truth table is obtained. Secondly, the truth table is factorized into two using BMF algorithm. Finally, two matrices are individually synthesized back to logic circuits, and then connected with each other. The factorization degree indicates the size of factorized matrices, which also affects the accuracy and size of approximate circuit. BMF is proved to be NP-hard. Thus, most algorithms take a heuristic approach. For example, the SO algorithm used the error framework. Such algorithm solves column of A and rows of B pair by pair. As more pairs are solved and factorization degree increases, the factorization error is monotonically decreasing. In this example, when factorization degree increases from 1 to 3, the Hamming distance is 7, 4, 2, respectively. Now let's discuss our Ruca methodology in detail. As discussed before, instead of a fixed approximate circuit, we want to be flexible. Let's do some simple maths. According to matrix multiplication rule, the product of factorized matrices capital A, capital B can be separated into sum of product of vectors AIBI. Heuristic property of BMF algorithm tells us that as we add more terms from AIBI to AFBF, in this case, the factorization error will never increases. Now, for example, we want to factorize the input matrix M such that two accuracy levels exist in the factorization, which are 2% error and 1% error. We start by summing AIBI terms until factorization error is no larger than 2%. Remember that as we sum those terms, the factorization error is monotonically decreasing. Imagine now I equals K1, then we might recombine those terms into capital A1, capital B1, which is effectively a factorization of M with error threshold 2%. Now we start working on accuracy level of 1% error, assuming as we continue summing AIBI terms, and when I equals K1 plus K2, we satisfy 1% error threshold. If we now recombine the new added terms as capital A2, capital B2, now capital A1, capital B1 plus capital A2, capital B2 is another factorization of M with error threshold 1%. In summary, if we factorize input matrix in this way, we may incorporate multiple accuracy levels within one factorization. Or in other words, we may think such multiple level factorization as a separation of original factorized matrices, capital A, capital B, into capital A1, capital B1, and capital A2, capital B2. As the example we've seen before, we can now have a two-level factorization with Hamming distance 4 and 2 separately. If more accuracy levels are expected, we could follow such pattern to obtain more separations. Now let's move from math to logic synthesis, where a runtime configurable circuit is synthesized from such truth table factorization. Boolean matrix A1, B1, and A2, B2 are synthesized separately as shown in the diagram, using the methodology of approximate computing with Boolean matrix factorization. Power gating is used to control the activation of A2, B2 block. To implement the addition algebra between two terms, bitwise OR gates is used to connect both blocks. For now, we managed to create a flexible approximate circuit with multiple accuracy levels. However, as mentioned before, since BMF is an NP-hard problem, it is not possible to obtain 100% accurate factorization, which means so far our design is not able to run in full accuracy mode. 100% accuracy can be important in many applications, so in order to implement the full accuracy level, an auxiliary circuit is needed. In Boolean algebra, we are able to obtain the difference between two matrices using XOR gates. So here, we compute a character matrix C by taking the XOR between the input matrix M and factorization result. Now, again, by using XOR, the character matrix C can be used to correct the inaccurate factorization result. Below is the previous example, but with an additional character matrix for self-correcting. Now we can amend the character circuit to previous framework. The character circuit is synthesized from character matrix C and connects with other components using bitwise XOR gates. The activation of character circuit is also managed by power gating. With such three-level configurable circuit, including full accuracy, the entire design has 3 blocks. The base block contains synthesized results from A1, B1, as well as connecting OR and XOR gates, which are activated by default. The base block supports the execution of accuracy level with largest error threshold, and is the base of all other accuracy levels. If you would like to reduce error threshold, the level 2 block is also activated. Finally, if full accuracy is expected, the character circuit is also activated, and now the functionality of original circuit is 100% restored. For runtime configurable circuit, an important criterion is design overhead, which is defined as additional chip area and power consumption running on full accuracy mode. In Ruca methodology, design overhead mainly comes from 2 sources. 1. To implement the addition algebra and the character circuit, additional OR and XOR gates are used. 2. Since blocks for different accuracy levels are synthesized separately, we may lose the opportunity of logic optimization across different blocks. More accuracy levels lead to more connecting OR gates and also contribute to the issue of such logical redundancy. So theoretically speaking, we can conclude that both sources of design overhead increases as the number of accuracy level increases. Another concern of our methodology is the scalability issue. As we know, the size of truth table grows exponentially as number of inputs, which also leads to an exponential running time of BMF algorithms. Thus, it is impractical to execute BMF algorithm on truth table of large circuits. Here, we propose the circuit partitioning and design space exploration method to improve the scalability. The first step is to partition the large input circuit into smaller ones. More specifically, we would like to continue breaking down the input circuit until all sub-circuits has a limited number of inputs and outputs, for example 10. After limiting the size of sub-circuits, we are able to generate runtime configurable design for each sub-circuit. Remember that the design overhead increases as the number of accuracy levels increases. Thus, for the runtime configurable design of each sub-circuit, we limit the number of accuracy levels to 2. This means that there is only a base block and the character circuit. Notice that here, what we limited is the number of accuracy levels of sub-circuits, not the top-level design. In the third stage, we assemble those base blocks and character circuits of subcircuits back into top-level design. Specifically, all base blocks go to the base block of top-level design, and all corrector circuits compose the full accuracy block, which restores 100% accuracy. However, if additional accuracy levels of top-level design are expected, more intermediate blocks can be created by rearranging the corrector circuit of subcircuits as this image shows. By these three steps, we break down the practical problem of factorizing a large truth table into the problem of factorizing multiple much smaller ones. To locate the specific subcircuits, a design space exploration method is applied. Finally, I will show the robustness of our methodology by some experimental results. We evaluated our methodology on a number of commonly used arithmetical benchmarks from Backus and EPFL benchmark with such setting. We use mean absolute error as error metric, which is effectively the average amount of relative error across all text vectors. We first experiment on a small benchmark, 8-bit adder, without circuit partitioning and design space exploration. The number of accuracy level is fixed to 2, which means there exists only one approximate mode besides full accuracy, and we choose different error thresholds as that one single approximate mode respectively. As the purple line shows, as the error threshold increases, the power consumption of corrector circuit also increases. That is because the corrector matrix gets less and less bars during this process. As green line shows, when error threshold increases, the power consumption in approximate mode decreases. If we accumulate those two numbers, we obtain the power consumption in full accuracy mode, which is the blue line. This power consumption seems to be stable at the very beginning, but increases dramatically after 3 to 5% error threshold. This is because the corrector circuit starts to dominate power consumption. In the second experiment, for the remaining 6 benchmarks in Backus, we generate 3 Ruca designs with 2 to 4 levels respectively, where error thresholds are set to 0.1%, 1%, and 2%. Since these 6 benchmarks are relatively large and their truth tables are difficult to be factorized directly, we adopt circuit partitioning and design space exploration method. Here, relative power is defined as ratio between power consumption of Ruca design and power of original circuit. Compared to original circuit, Ruca substantially saves power under approximate mode. However, for full accuracy mode, power consumption increases as the number of accuracy levels increases. As we analyzed before, this is because design overhead increases as number of accuracy levels increases. Finally, we evaluate our Ruca methodology on all benchmarks to generate 3-level designs with 2% and 1% error thresholds, and compare against another runtime configurable approximate framework, approximation through logic isolation. Briefly speaking, logic isolation method dynamically configures accuracy levels by identifying isolated logic islands and controlling their activations. This table shows the comparison. Red numbers represent that our results are better, blue numbers represent that it's worse. In terms of total area, our methodology has better results in 6 out of 9 benchmarks. For power consumption, under full accuracy, our methodology has better results in 8 out of 9. This demonstrates that our Ruca methodology ends up with less design overhead because there is no need for large number of multiplexers. However, with 2% error thresholds, Ruca has only 4 better results out of 9 because with higher error threshold, logic isolation is able to shut down more cells from original circuit. In conclusion, we propose a methodology Ruca to generate approximate circuit that is able to configure accuracy power at runtime. By properly separating truth tables, we are able to implement multiple accuracy levels within one approximate circuit, and the corrector circuit is introduced to fully restore original functionality. We also adopt circuit partitioning and design space exploration method to improve the scalability. This is the end of my presentation. Thank you for attention. Please feel free to ask any questions. Thank you.